All right, let's go ahead and begin. Welcome to our Coherent Communications webinar. My name is Dan Henme, VP of Sales at Quantifi Photonics, formerly known as Coherent Solution. And we're very excited to have you attend this webinar with our exclusive OMA partner, Tektronix. And this webinar will last about 1 hour. And after the webinar is finished, you will receive an email with a link to the recorded webinar. A few housekeeping items before we start. First one is you will all be automatically placed on mute, and you will not be able to speak during the presentation or ask questions. Instead, you'll have the opportunity to ask questions in the chat window. And if you see an arrow on the right-hand corner of your screen with an arrow and a vertical line, if you open it in that capacity, you can put your questions in that particular chat area. Okay, and now questions will be answered at the end of the presentation. So at this time, I'd like to introduce Dr. Sung-Hoon Im, who is presenting Coherent Communications, selecting the right OMA for your needs. So Sung-Hoon.
Hello, everyone. This is Sung-Hoon Im. I'm the Director of Technical Sales at Quantifi Photonics. As Daniel mentioned, we've had a name change last year. So for those of you who know of us as Coherent Solutions, we are now Quantifi Photonics. And last year also, we've had a new partnership, an exclusive partnership with Tektronix. And now our OMA system is offered with Tektronix real-time oscilloscope. Okay, so today we'll get started with a quick overview on the coherent communications market, comparing the coherent technology with the non-coherent counterpart. And we'll briefly touch on the challenges involved with measuring coherent signals. And I'll introduce you an OMA system that can maximize your return on investment on your OMA purchase. And then we'll continue on answering the question, how much bandwidth do you really need in an OMA for the measurement you are trying to make? So let's get started. Coherent communications. It's been used for long-distance communications traditionally, such as submarine links, long-haul links, spanning thousands of kilometers. That's because the coherent technique can offer really high data rate per wavelength, up to 400 gigabps. And then you can multiplex that with multiple wavelengths to achieve even higher aggregated rate. Now, the hardware cost involved with coherent technique is higher as it involves multiple extra layers of complexity, but for applications where laying the fiber comes at a really high premium, like the submarine cables, the advantage of having the highest data output, even though the hardware itself may be a little more expensive, found its place. And also, the coherent technique uses DSP, digital signal processing. So physical effects like dispersion can be mitigated from the DSP's function to compensate for the dispersion. So in the submarine cables, you don't need, the repeaters every so, hundreds of kilometers. And it's a really ideal application for coherent technique. Now, for shorter distance links, non-coherent transceivers have been used traditionally as it is cheaper and it is more simpler. And laying the fiber, an extra fiber is, that works out to be cheaper than trying to go to adopt the highly complicated coherent technique. That's been the tradition. Now, with the population taking up video streaming and gaming and connecting multiple devices to the internet, the data demand in the data center, the bandwidth demand has grown exponentially over the years. And what this is driving is we are starting to see the coherent technology being adopted for shorter distance links, such as the data center interconnect. And OIF has recently released their latest standard 400G ZR, which is aimed at just that. 120 kilometer link, ideal for data center interconnect, utilizing the coherent modulation technique. And that's now coming in a very small form factor transceiver, such as QSFP-DD. OIF also states a secondary application, a point-to-point unamplified, potentially low-cost version of their 400G transceiver. And this could even be a solution for intra-data center connectivity. So we can see that the coherent technology is now moving into shorter distance links. So how does coherent technique differ from the non-coherent counterpart? So on the left side, you have a diagram showing you the conventional NRZ or on-off keying modulation format. So when the light is on, it indicates the bit of 1. When it's off, it indicates the 0 bit. So you can see that one symbol or baud can only represent 1 bit. Here you are modulating the intensity of the light. So it's pretty straightforward to measure and detect. You use an oscilloscope, whether it's a real-time oscilloscope or sampling oscilloscope, with an optical to electrical converter. And straight away, you can get eye diagrams, you can get raw traces, and you can continue to measure bit error rate and diagnose the signal. On the right-hand side, you have an example of a coherently modulated QPSK signal. In this example, you are modulating the 360-degree phase into 4 separate segments, which are 90 degrees from each other. So now you have 4 different symbols, of which can represent 2 bits of data. So by modulating the phase, you have now multiplied the bit rate from the same baud rate by a factor of 2. So this is a great way to increase the data throughput while keeping the baud rate and the associated hardware bandwidth and specs about the same. But this advantage comes at the cost of additional layer of hardware complexity. You need to use an optical coherent receiver, which is a lot more complicated than just the O-to-E converter. And you need to use the real-time oscilloscope to measure the contiguous data so that you can recover the phase modulation information from it. You also need to use digital signal processing to recover the modulated data, and it all adds to the complexity of the coherent signal. Now, in terms of how you diagnose a complex coherent signal, you don't just get the eye diagrams and BER. There are constellation plots, there are recovered traces of 4 independent tributaries instead of just 1. You have measurement parameters such as error vector magnitude, EVM, bias errors, BER, of course, and many other coherent-related parameters such as frequency offset and hybrid 90-degree offset and more. But coming back to the advantage of being able to multiply the data rate for a given baud rate, here let's have a look at the chart to see what examples of modulation format can achieve in terms of boosting that data rate. So on the left, you start with the NRZ, which is a non-coherent format. So you have the 1-to-1 ratio between the baud rate and the bit rate. As you go up the scale, all the way up to 64 QAM, where you have 64 individual symbols, now here you're achieving 6 bits of extra data for a given baud rate. So you can see that now 64 gigabaud signal can get you up to 768 gigabps, which is a significant increase in the data rate. So we've seen the benefits of the coherent signal and the layer of complexity that it adds. So how do we test such a signal? So let's have a look at what's typically involved in a coherent communications test bench. Now, from the left, you start with an RF signal generator, which will generate 4 independent channels of high data rate electrical or RF signal, which will then drive the optical coherent transmitter. Inside the IQ transmitter, you'll have a laser as the source. You'll have an IQ Mach-Zehnder modulator, which is polarization multiplexed. So you have dual pole IQ modulator. And there'll be high bandwidth linear driver amplifier to boost the voltage to the appropriate levels needed by the modulator. And then, of course, you have the automatic bias controller, which will take care of controlling the 6 bias points involved with the IQ modulator. It's not just one like the non-coherent modulator. IQ modulator has 6. And you're having to control all that from one modulated optical signal. So it has to involve very novel techniques to do that. On the receive side, you have the coherent receiver, as you can see in the flat box in the middle, paired with real-time oscilloscopes. Because coherent modulation format involves phase modulation, you cannot, or it's not easy to use sampling oscilloscope. You have to use real-time oscilloscope to capture contiguous data so that you can recover the phase differences. You need the OMA software, which has the DSP capability to recover the signal once the raw data has been captured from the OMA hardware. And on the receive side, you also need another laser, narrow line with tunable laser, to use as an unmodulated reference signal source. If we have a look at the functional diagram of the IQ coherent transmitter, you start with 4 independent lanes of RF signal. So you can have NRZ, PAM4, or PAM8, depending on what type of optical coherent modulation format you want to achieve. If you start with NRZ, you'll get QPSK. If you start PAM4, it ends up with 16 QAM, and PAM8, of course, leads you to 64 QAM. Now, all these 4 levels or data streams will get mixed into one optically modulated signal. So you can see now when you generate such a signal from the transmit side, as it travels down the optical fiber, at the receiver, now the 4 tributaries or the 4 independent lanes of data are now mixed up because your receiver does not know which is, say, X polarization or Y polarization. It doesn't know which is I or Q. So the receiver splits it into its own 4 tributary outputs, but the signal actually is a mixed in various proportions. So what your receiver thinks is an Xi tributary will contain components of Xi, Xq, Yi, Yq tributaries from the transmitter. So until you decouple and realign these receiver tributaries to match that of the transmitter, you won't be getting a meaningful data out of your receiver or OMA. Now, this untangling or decoupling is performed in DSP, in digital signal processing. So if you have a look at the functional diagram of the coherent receiver and the OMA, the modulated signal input gets split up into 2 hybrids, and now it's converted to 4 tributary electrical signals. As I mentioned earlier, at this point still, the tributaries are still mixed up And the real-time oscilloscope shows a raw data that's actually not presenting anything meaningful, because it's a mix of the 4 transmitter tributaries. So if we have a look at the DSP chain that needs to happen in order for you to recover and see the meaningful data that was transmitted, you start from the left with the raw data from the oscilloscope. The DSP performs hardware calibration to compensate for any hardware impairment or characteristics, such as the receiver skew between the 4 channels, hardware S21, the frequency response, and various other hardware characteristics can be removed to ensure optimal signal measurement. If your signal has propagated through a long length of fiber, it will have undergone linear chromatic dispersion. So you can compensate that from the DSP. It's a linear process, so you do it upfront. You can just reverse that dispersion. But even after that, your signal is still a mushy signal because your X and Y polarization is still mixed up. So after you decouple them using the pole demux, you start to see a constellation that forms various levels of amplitude. Now, the constellation is still rotating because there is a difference in frequency between the signal and the local oscillator laser. No laser can have absolutely the same frequency, so there always will be some rotation. But that rotation can very easily be removed in DSP, and after you've compensated for that frequency offset, now you have a constellation that's not rotating, but still exhibits some rotational smudge originating from the phase noise of the laser. So yet again, you use the DSP algorithm to remove and compensate for that phase noise, and you end up with a nicely measured constellation of the coherent signal. So all these stages of DSP has to be performed in an OMA. A good OMA will provide you with a software that has the DSP steps built in, so that users can easily configure DSP and come to seeing the meaningful signal information. The software, in addition to the DSP algorithms, the software gives you visualization, various graphs such as the eye diagram, constellation plot, spectral plot, polarization plot, and give you numerical measurement parameters such as transmitter characteristics, the bias errors, the imbalance, and EVM and BR, of course. Here is an example of the OMA software that we offer. And it gives you a control panel with all the DSP algorithms that user can configure all in one place. And it makes it easy for a non-specialist user to get going with the algorithms and start the measurement. It also provides you an extensive list of numerical parameters so that you get a true insight into your signal's characteristics. For advanced users, the OMA software also has the MATLAB interface integrated into the processor. Now, this gets executed in real time. So when you add MATLAB command and you acquire a sweep, then each sweep, the new command set is applied and executed. So if you're testing your DSP, or if you're wanting to try some customization to the DSP, you can see the impact or the result immediately. And it's a great way to save time in your development. So let's have a look at the ways to maximize the return on investment of your OMA purchase. So as you've seen, an OMA consists of a multi-channel, high bandwidth real-time oscilloscopes, which are not cheap. And when you invest in such hardware, being able to repurpose this high-end instrumentation will bring a lot of value to your purchase. There are OMA systems which is built to just do one thing as an OMA. Now, our OMA system has been configured so that the customers can utilize the real-time oscilloscope for other measurements other than OMA measurements. You have 2 or 4 sets of high bandwidth oscilloscope, which you can decouple from the OMA system and use it to measure electrical signals, say PAM4 or PAM8. Now, in your R&D environment, of course, before you turn the signal into an optical signal, you have to diagnose and optimize your signal from the DAC or AWG. So being able to measure the electrical signal and try to diagnose and optimize is a great added benefit that will speed up your development. If you add an auto-E converter, you can, of course, use the oscilloscope for optical PAM4 or PAM8 measurements. There's a transceiver development happening for PAM4 modulation format, and that's a hot topic today. So being able to share and reutilize the oscilloscope hardware for such applications is, again, is maximizing the return on your investment. Now, the reason that we are able to offer this level of flexibility is because we've made the coherent receiver to have 2 built-in tunable lasers. Now, normally, a coherent receiver will just need 1 laser to use as the unmodulated reference signal source. But the second laser, paired with the function in the software, enables the customer to perform user calibration of the hardware characteristics, such as the channel skew and frequency response. So when you have finished using the oscilloscope for other purposes, you put it together as an OMA system, reconnect the cables, and you can perform the cable channel deskew yourself using the 2 built-in lasers, and you don't have to worry about changes to the channel skew, which could have a significant impact on your signal measurement. Now, in addition to being flexible, the modular architecture of the Tektronix SX series oscilloscope gives you this unique upgrade path. So if your requirement today is not all the way up at 70 gigahertz, you can configure a 33 gigahertz OMA using 2 of the SX series oscilloscope stack. And in the future, if you need higher bandwidth or if you need more number of channels, you can simply add 2 extra modules of the oscilloscope, giving you a seamless path to future-proofing and to upgradability. The SX series has options to offer you 1 high bandwidth channel or 2 lower native channels. For example, this one, you can see it has 1 70 gigahertz channel or 2 33 gigahertz channels, so that even when you're configuring it in the 33 gigahertz dual pole OMA, you can still have access to 2 of the 70 gigahertz channels to enable single polarization measurement at 70 gigahertz, giving you a sneak peek at the higher bandwidth measurement. When you're ready to go full dual pole at that high bandwidth, that's when you just need 2 extra oscilloscopes. All right, so choosing the right OMA Now, here we'd like to answer the age-old question, how much bandwidth do I need in my OMA? So to answer this question, I'd like to divide the applications into two different environments. So there's the R&D environment and the production test environment. The two applications have very different priorities. In R&D, your priority is to make most accurate measurement of your optical signal possible. You want to know any defects or any impairments that exist in the signal, and you're often using the signal measurement to debug your transmitter's performance. So it is important for your receiver hardware or OMA not to distort the signal's spectral properties. And in order to do that, you need more than sufficient bandwidth, more bandwidth than your signal has. In the production test environment, on the other hand, the priorities are to perform pass-fail test, quickly automated, and have an OMA test hardware that's low cost. So it is not of the interest to have the highest bandwidth available in an OMA. You want just enough bandwidth to keep the cost low. That will ensure that you're making an accurate EVM or BER measurement so that you can pass or fail your device under test. Sometimes your device under test uses Nyquist filtering, which restricts the amount of spectrum contained within the signal. So being able to mimic the spectral characteristics of your DUT receiver is another application that may be of interest in production test. So for R&D environments, it's actually quite simple. So you want the highest bandwidth OMA. Now, before we go into how much bandwidth you need for R&D, let's have a look at the signal consideration. So basically, your OMA has to have more bandwidth than your signal's bandwidth. On the market today, if you look at what hardware is available on the market to generate your coherent signal, let's start with the AWG. So there are new model AWGs released on the market with up to 45 gigahertz of bandwidth. And you pair it with an IQ transmitter with, again, up to, say, 45 gigahertz of bandwidth. Now, even for the OIF standard high bandwidth coherent driver modulator, which is an all-integrated transmitter module for commercial purpose, the standard specifies greater than 35 gigahertz bandwidth. And typically, we're seeing new models from vendors coming in with, say, 55 or even up to 60 gigahertz of bandwidth. And the use of pre-emphasis in the AWG can further boost the signal bandwidth higher than what the hardware offers. So you can see the signal type, the kind of coherent signal you can generate today will have around 50 to 55 gigahertz of bandwidth. So a 70 gigahertz OMA will provide you distortion-less measurement of your signal, as it has a lot higher hardware bandwidth than your signal has. And it'll also future-proof for any upgrades in the future on the transmit side. And you'll be future-proof to measure up to 140 gigabaud of signals in the future. Now, again, if you don't need all this 70 gigahertz of bandwidth today, there is an upgrade path available. So you can start from a lower bandwidth configuration and move up in stages. Now let's have a look at the requirements for production test. So your natural question would be, what is the minimum bandwidth I can get away with, say, to measure a 400 gigabps signal. So let's have a look at through the use of this constellation plot example showing you your QPSK signal when there's when there's sufficient bandwidth, greater bandwidth than the signal itself on the top, and when the OMA hardware's bandwidth is limited. So you start to distort or filter out some of your signal's bandwidth. Starting from the left, it's an optimized QPSK. When there's sufficient bandwidth on the OMA side, your trajectories, your transitions are very sharp. It's very, very confined, and it's a beautiful constellation. When you start to cut into your signal's bandwidth with the use of a limited bandwidth OMA, your trajectories start to lose this sharpness. Similarly, if your signal started with a chirp, when you measure it using a high bandwidth OMA, you will see this twirl in the trajectory, which is an indicative sign of the chirp that's present in the signal. When your OMA doesn't have enough bandwidth, this information about the twirl or the chirp is lost as the trajectories get fuzzier and it becomes less sharp. Similarly, when the transmitter has data skew between I and Q, it's easy to tell from a high bandwidth measurement that the inner trajectories start to split up like this, and that information will be lost if you start to filter down with the limited bandwidth OMA. One thing to notice here, though, as you use the limited bandwidth OMA, you're losing the trajectory, accuracy, and information. But if you just look at the constellation points, which is captured at the center of the eye, the constellations are not as heavily affected by this limited bandwidth measurement. So in the production test application, if your interest is just on measuring EVM, which doesn't care about the trajectory, or BR, then using a limited bandwidth OMA hardware is an acceptable solution. You still get good EVM measurement. You can still perform pass-fail test. You can still check on the health of the ODOG. Now let's move on to the topic of Nyquist filtering, which is a spectral filtering often employed by transceiver manufacturers. So on the left here, it shows you that for a given baud rate, depending on your signal's profile or shape, you can occupy a widely varying amount of spectrum. So if you have a nice sharp square waveform, your spectral occupation will be very broad. But if you have, say, raised cosine profile, your spectrum will be very much narrower. So in order to increase the spectral efficiency and occupy as little spectrum as possible, the raised cosine profile is often employed by the transceivers, and they shape their signal to this profile. The raised cosine spectrum has a property called the roll-off vector, and it determines how rapidly you're rolling off and you're chopping down your spectrum. So if you have a roll-off factor of 1, which is a very broad spectrum, you can see the light blue color, that's the most wide spectrum, all the way down to a roll-off factor close to 0, where it's very tightly confined to a Nyquist limit of signal bandwidth. And of course, as you come down in the roll-off vector, your signal properties look more like this raised cosine profile. So let's have a look at the impact of what the limited bandwidth OMA has on your signal measurement. If we use a 31.5 gigabaud coherently modulated signal, from the baud rate, you can expect the fundamental frequency to be, which is half this baud rate, to be just under, 16 gigahertz. So if you have an OMA with 16 gigahertz bandwidth, your signal measurement is very clean, very nice, with very little distortion. Now, if you go down a bit further so that you're under the half baud rate frequency at 14 gigahertz, you start to lose a little bit of accuracy. Your constellation becomes a little noisier. But then just moving 1 gigahertz further down, you can see that the signal degradation happens really quite quickly. If we were to plot this on a graph with the following test conditions, so again, using the same type of signal in different formats. So you have the QPSK, 16 QAM, 64 QAM signals, using 0.2 roll-off vector, which is typically employed in the commercial transceivers, and use various OMA bandwidth settings to see what kind of impact it has on the EVM. You'll see that all the way down to 0.5 vector, which means the scope bandwidth is half of the baud rate, the EVM penalty or impact is quite minimal. But as you go below 0.5, you quickly start to see that the EVM penalty becomes quite pronounced. So now, if we assume that in the production test environment, you're trying to test a commercial transceiver with Nyquist filtering, let's have a look at what baud rate can be measured using a 33 gigahertz OMA bandwidth. Now, in this diagram here, it looks similar to the one you've seen before, which was for raised cosine spectrum profile, but this is the root raised cosine spectrum. The reason I'm showing you the root raised cosine is that to achieve overall raised cosine profile, you're applying the root of it, basically root of it on the transmit side and another root of it on the receiver side, so that when the signal is measured, the overall effect is that you're gaining the raised cosine profile. Now, so on the OMA side, if you have a look at the root raised cosine, you'll see down at minus 3 dB point, which is the half intensity point, depending on the roll-off vector, your spectral bandwidth varies a little bit. And you can see that with the smaller roll-off, your spectral occupation is quite small. But as you increase, you start to occupy a broader spectrum. So if you plot a table with this, and if you find where the 33 gigahertz lands, and if you want to capture the spectrum down to the 3 dB point to ensure accurate measurement, you end up with this table. So with a varying roll-off vector, the baud rate you can measure up to with a 33 gigahertz digitizer varies like this, from 60 gigabaud to 64.7 gigabaud. So with the roll-off vector of 0.2, commonly employed by transceiver manufacturers, your 33 gigahertz digitizer will enable measurement up to 62.26 gigabaud. A real-life measurement example of a signal from a commercial 400G transceiver operating at 63 gigabaud is shown, and you can see that we're kind of approaching the limit of what a 33 gigahertz OMA bandwidth can measure. But you can see that it's giving you a good measurement that'll enable you pass or fail test of your DOT. And of course, there are many other commercial transceivers which employ a lower gigabaud rate to achieve 400G. Now that depends on how much overhead you want to leave in your signal. Now, in addition to determining the amount of bandwidth you need, another important factor to consider is the EVM noise floor. So as your modulation format becomes more complex and higher level, you're packing more and more number of symbols onto your IQ plane. What that means is now the distance between your symbols are closer together. So when your measured constellation lands on a point far away from its reference location, there's a potential to switch to the next reference location, and that distance is the margin. And as you can see, by comparing the example of 16 QAM and 64 QAM, that margin is significantly shrunken in the case of 64 QAM. So the distance between the symbol before you switch to the adjacent symbol is only 10% EVM. So that's kind of the upper cap of what your EVM can go up to. So it's easy to see now that any noise floor or minimum hardware noise in the EVM measurement will impact how accurately you can measure your higher level modulation format. And having the lowest noise floor possible in an OMA will ensure you that you can accurately measure and characterize your higher order modulation formats. Now, we have designed our OMA with this in mind to ensure the EVM noise floor is kept as low as possible. We've excluded the use of TIA in the coherent receiver to ensure the minimal addition of noise, and pairing it with a low noise real-time oscilloscope and using shielded construction in the coherent receiver, we have managed to achieve the industry's lowest EVM noise floor spec of 1.3%. So this is something to keep in mind when you're making decisions of OMA. If you're intending to measure higher order modulation formats, this will really help you make that accurate measurement. So I hope this has been educational. I hope the age-old question of how much bandwidth do I need if I just want to measure it in the production test environment with minimal bandwidth possible. I hope it gave you some insight into what consideration factors to think about when you're answering that question, and hope it makes you an informed decision about your OMA purchase.
Thank you, Sung-Hoon. I really appreciate it for the presentation. At this time, we don't have any questions, but for those that may have some questions now, if you look up the top of your screen where there's an arrow, you just open up that chat room there and you can ask the question. So we have a few more minutes now. If you'd like to do that, we can wait a few seconds to answer questions. If not, you will see the slides not slides, but you'll see the presentation, video presentation emailed to you after this is over. So you will have a copy of the video. So please type in your questions if you have any at this point.
You'll also see the email address on the screen, sales@quantifiphotonics.com. If you have any inquiries or questions after the webinar, please feel free to email us, and we'll do our best to answer you immediately.
All right, Sung-Hoon, I don't see any other questions. So we really appreciate everyone joining the call today. And again, if there's any further questions, type in the email and get a hold of us, and we'll respond to you immediately. All right. Have a great week, everybody. We'll talk to you later. Bye.
Thank you very much. Bye-bye.